Hello everyone. If you're watching this on YouTube by random chance, I'd love to know how you got here. Leave a comment. But the more likely scenario is, thank you to the marking staff who were watching this. The feedback from the first assignment was very helpful, so much appreciated. Down to brass tacks. Assignment number 2, User Authentication and Access Control. A presentation for Monash University. My name is Oscar and I'm a second year student. This video covers all the sections of the assignment and I'll have chapter markings in the description. The first section is two-factor authentication, subsection biometric authentication. This part used a Ubuntu virtual machine containing Exadel's Comproface running in Docker. The VM was a VirtualBox container, but there were some issues along the way, so I extracted the disk from the OVA file provided and turned it into a Hyper-V virtual machine from there, using a script by GitHub user Hinara to provide guest extensions which help with performance. Following the instructions provided, I added 5 photos of myself to the dataset. Then I used the test utility to check 10 photos of myself against the database, recording the certainty values provided by Comproface. I also used 10 photos of another individual not in this database, Ryan Gosling. This is to test how good the machine learning software is at discerning people apart, and this testing is in the name of security, because what we found is that Ryan Gosling and I are in fact not confused for one another. On the upside, we found remarkably good recognition performance, but first, a few clarifications. Those certainty values from before are on a scale of 0 to 1, and we're using 2 thresholds in these tests, 0.95 and 0.98. Values greater than or equal to these thresholds are accepted, meaning that the software has authenticated a given face as the person it's named. False acceptance rate, FAR, is the percentage of faces that the software incorrectly assigns to a person above those thresholds. And on the other hand, false rejection rate, or FRR, is where the computer has incorrectly not accepted a given face as a person. The results are here, and I'll explain them. With a threshold of 0.95, it's easier for a face to be accepted, whether that be incorrectly or correctly. So a higher threshold is more secure, but possibly less convenient. So we'll go with 0.98 as our threshold of choice, where false acceptances drop from 30% to 0, and false rejections only escalate from 10% to 20%, which is a good trade-off. Next section, password authentication, namely password cracking. We can see the procedure here using John the Ripper, a command line utility with a built-in password dictionary. The tests I ran on the 4 supplied password hashes are on screen now. They varied in rounds and salting, and we can see that through those 5,000 round tests, salting doesn't make much of a difference in computation time. Next is password hashing, where I use the same values, 1,000, 5,000 and 50,000 rounds, with one of the 5,000 rounds having no salting, to hash passwords with the make password utility. The results show that just like with password cracking, there is an upward correlation between rounds and computation time, because more rounds is more processing. We can also see that the sheer difference in computational complexity of hashing a password versus cracking it. If we average the time for each of those 4 tests, it's almost 2,500 times more computationally intensive to crack a password versus hashing one. We can also extrapolate the time taken to crack a password based on dictionary size. In John the Ripper, the C/S value represents how many passwords the software is trying every second, and it tries passwords out of a dictionary. We can once again average out values from each of our tests and use that as the divisor of a dictionary size. In this case, given a dictionary of 200 million passwords, it'd take nearly 60 hours to work through that. Salting prevents an attacker from pre-computing hashes to passwords in the dictionary with minimal cost on hashing performance, so it should always be used. As for how many rounds should be used, that depends on the application. But with a per password random sort of a decent length, it should be so unrealistically likely to find a random password by brute force that there should be no need to go beyond the default of 5,000 rounds. Next is access control, where I followed the instructions to create user accounts. I found that it's not possible for Peter to modify either hr.txt or it.txt. The reason for hr.txt is because Peter's account is in the IT group and not the HR group, and Peter cannot modify it.txt despite having the correct group assignment for that folder, because Mary created the file, so by default it has read-only permission for all users, and write permission is only given to users in the Mary group. Next, the assignment asks for the UID of the program to be set. I'm not exactly sure what that means, but I changed all the files in the read secret directory to be assigned to the IT group, and then I changed the permissions of the executables so that the programs can be read and executed by IT group members. I also changed the permissions of the secret.txt file so that it's readable by the owner and the IT group, but nobody else. For the last task, I found that the employee directory can be written to by any user, and the file within can be read by anyone, meaning that Peter can read the contents of the file, delete the original file, substitute it for a new file with whatever contents he might choose, and then hypothetically mask doing this by amending the group permissions and ownership of this new file to match those of the former file. This can be corrected with a simple chmod command, which is on screen now, because the directory and file themselves already have the correct group assigned. It's simply a matter of changing the permissions. So that's the end of this report, and thus the end of this video. Thank you for watching, and like and subscribe.